Okay, in this video we're going to take a look at differentiation and integration of vector-valued functions. So previously we looked at what a vector-valued function was. You plug in a real number for t, and the output is a vector. And then we also looked at how to find the limit of such functions and determine continuity at a point and on an interval. So we're ready to tackle the derivative and antiderivative of a vector-valued function. And it's going to look very, very familiar to what we've already done with just a traditional real valued function. So we're going to start with the definition of the derivative for a vectored value function. So again, going to look very, very familiar. So the derivative of a vector valued function r is denoted r prime. We can use the prime symbol again, and it's going to be the limit. It's going to be the limit as the change in t approaches 0. And then we're doing the limit of what? Well, we're doing the limit of the difference between the vector valued function evaluated at t plus delta t and the vector valued function itself, so just r at t, all divided by the change in t. In other words, we're finding the change in the outputs of the vector valued function divided by the change in t itself. But we want the change in t to shrink towards 0, and then we're going to find that limit. This mimics the definition for the derivative of a traditional real valued function, so this should not be a huge surprise. Now, of course, the derivative only exists if this limit exists. So we need that limit to exist for the derivative to exist. Now, just like we did with regular real valued functions, we started with this limit definition, but then we used it to generate some shortcut formulas for derivatives. And we can still use those, and those are still in play because the left and right components of a vector value function are just regular real valued functions themselves. So all those shortcut rules we've learned are still valid. So with that in mind, this is how we actually will differentiate a vector valued function. We're not really going to work out that limit necessarily. So if r of t is defined as f of t times the standard unit vector I plus g of t times the standard unit vector j, let's say that's our definition for the vector valued function r. We just need f and g to be differentiable. The functions themselves, f and g, need to be differentiable. Then to find the derivative, we can just use shortcut formulas to find f prime and g prime. Now remember, the AP exam doesn't use the IJ notation. They're actually going to use this component form, which is why I've got it circled in red here. So for us, what we are basically going to do is, if we want the derivative of a vector valued function, we're just going to do the derivative of the left component and the derivative of the right component using shortcut rules. We don't have to work out that limit definition. So finding derivatives will be fairly straightforward, provided we remember our shortcut rules. So let's go ahead and take a look at how the derivative plays a part in the graph. So for this, let's go ahead. We're going to first sketch the curve for this vector valued function r, which is t comma t squared plus 2. So let's do that real quick. So the left component, x, is just t, and the right component is y, so y is t squared plus 2. But if x is t, then that just gives us y equals x squared plus 2. So that's just a parabola shifted up 2. So we're going to be here. So let's graph that real quick. So then you would go, if you plugged in -1, you'd get 3, 3. If you plugged in -2, you get 6. So the parabola itself, we would just look like this. But remember, it's a vector value function, so there's orientation. So let's see what the orientation would be. Let's say t was -2, then you'd be at 6. So if you're at -2, 6, then you plugged in -1, you'd be at 3. So it's moving kind of left to right. So our orientation is in this direction. Now I'm going to leave this part of the parabola kind of empty. I'm not going to put any orientation on there. You'll see why here in a sec. So this blue curve is the vector valued function itself. Now, let's go evaluate the vector valued function at 1 and see what that output is. So if I take the vector value function and plug a 1 in, I'll plug a 1 in there, I get 1. Plug 1 in there, I get 3. So 1, 3, starting at 0, 0, I'd get this vector whose terminal point would be 1, 3. So that red vector corresponds to the terminal point 1, 3, which is on the curve. We talked about that last time. That's how you graph a vector valued function. So no surprise there. Now why did we need that? Well, we want to now plug 1 into the derivative of this vector valued function. So let's go see what the derivative would be. So the derivative of r is just simply going to be the derivative with respect to t of t, and the derivative with respect to t of t squared plus 2. So the derivative of this vector valued function is just simply going to be 1 comma 2t. So just use our shortcut rules. Derivative of t is 1, derivative of t squared plus 2 is 2t. Now, if I plug a number into that, say 1, it'd be nice if there was some sort of similarity between this output and what we already know when it comes to traditional functions. So normally if you find the derivative of a traditional function and you plug in a value of, say, x, the output is the slope of the curve at that point, or the slope of the tangent line at that point. So we'd like it, it'd be really nice if we had some sort of similarity here for vector valued functions. And it turns out we do. So earlier we found this, where we plugged in 1 to the regular vector valued function and got 1, 3. We got this terminal point right here. Now it turns out that's going to be the initial point when we go to plot this vector down here. So the terminal point of r evaluated at 1 is going to be the initial point for the derivative of r at 1. And then the 1, 2 is how we go find the terminal point. We're going to move right 1, and then we're going to go up 2. So we're going to go right 1 and up 2. So this vector here, this green vector, that is r prime at 1. And as you can see, that green vector would behave or look like it's tangent to that curve at 1. But to get it, you got to think about it a little bit. You need the terminal point of the original function evaluated at 1, so you know where to start drawing the derivative vector. Then the output of the derivative at 1 is how you move, starting up here, how you move to get the terminal point of that derivative vector. So we went right 1, up 2. Right 1, up 2. So to graph, you start at r of 1, or I guess we should be more specific. We start at the terminal point of r of 1 and move 1 unit right and 2 units up. And that's how we would graph the vector corresponding to the derivative of r at 1. Okay, so just like with parametric, we want to make sure we understand what it means to be smooth, to have a smooth vector valued function. So again, it's going to mimic what we already know. So to be smooth, there should be no abrupt, which spelled wrong, should be no abrupt changes in direction on its graph. So no sharp turns, no cusp-like objects. More specifically, we need f prime. So remember, our vector valued function, f is the left component, g is the right component. So f prime and g prime must be continuous on the interval and f prime and g prime can't both be 0. In other words, there can't be a value of t where the output would be 0, 0. All right, so let's go give that a whirl. Let's see if we can't figure out what they're trying to say there. It's basically exactly the same as it was for parametric. We need f prime and g prime to both be continuous on whatever interval you're interested in, and that we can't have them both be 0 at the same time. So, matter of fact, let's just go do, I think this is the same one from when it was parametric, just to kind of reiterate that vector valued functions and parametric equations all are very, very similar. All right, so let's get the derivative of this. So if I get the derivative of r, so we're just going to do the derivative of r, which is up here. We would get negative 5 sine of t plus 5 sine 5t. And then the derivative of the other component would be 5 cosine t minus 5 cosine 5t. So as you can see, the left component, f prime, it would be continuous for all real numbers because it just involves the sine function. And the right component, g prime, would be continuous for all real numbers because it just involves the cosine function. So f prime and g prime are continuous for all real values of t. So we're good. So it's definitely, they're both continuous on the interval. Now, are those derivatives ever both 0 at the same time? And it turns out they are. So if you do the derivative, it actually will output 0, 0 when t is equal to 0, pi over 2, pi, 3 pi over 2, and 2 pi. So that, remember, our domain's restricted to be 0 to 2 pi. And it turns out all the quadrantal angles will cause this to output 0, 0. So if you don't believe me, just try it. Cosine of 0 would be 0, so you'd have 5 minus, plug in 0. Oh, wait, that's the original one, sorry. Let's go plug it into the derivative, that would help. Sine of 0 is 0, sine of that is 0, add them together, you get 0. Cosine of 0, you get 1, so that'd be 5 minus 5 is 0. So and it'll be true for those other values of t also. So we can now conclude that the original vector valued function is smooth on the following intervals. 0 up to pi over 2, not inclusive. Pi over 2 up to pi, again, not inclusive. Pi to 3 pi over 2, and then 3 pi over 2 up to 2 pi. So, if we wanted to integrate this vector valued function, which we're going to talk about here soon, I'd have to split it up and integrate separately on those intervals. So if I was going to do some sort of definite integral, I'd have to split it up and do it on those smaller intervals if I wanted to do 0 to 2 pi. Well, speaking of integration, how are we going to integrate? Turns out it won't surprise you in the slightest. So let's say your vector valued function r is defined to be f of t, g of t, where f and g are continuous. On some interval a to b, and it could be from negative infinity to infinity, but we'll just say it's continuous on some interval a to b. Then turns out if you want to do the antiderivative of the vector valued function r, you just simply do the antiderivative of f with respect to t and the antiderivative of g with respect to t. So you just do the antiderivatives of the components individually, and voila, you get the antiderivative of the whole vector valued function. And if you had a definite integral, which is why we needed continuity on the interval, again, no surprise, you just do the definite integral of f and g individually. So no new fancy formula, nothing kind of out of the ordinary. This works pretty much as you would hope it would. Since we already have enough we got to keep track of so far in the course. So let's give this a whirl. Let's do this definite integral. Let's do a definite integral for this vector valued function here. It uses the ij notation, but we'll switch it. So let's say we want to do 0 to 1 of, instead of the cube root of t, we'll do t to the 1/3. We'll switch into the component form like the AP exam would use. So all I got to do here is just do the definite integrals of these individually. So in this case, I would just be doing 3/4 t to the 4/3 from 0 to 1, and then natural log absolute value t plus 1 from 0 to 1, and I'm going to end up with the vector 3/4 natural log 2. So normally if you do the definite integral of a traditional function, the output is a constant, some real number. In this case, when you do the definite integral of a vector valued function, the output is just a vector in component form, but a constant. No variables. So for this one, let's find the antiderivative of this vector valued function that satisfies this initial condition. So if I want r itself, I would just simply do the antiderivative of r prime with respect to t, and using component form, it would look like so let's see, what would that turn out to be? We would just have to do the antiderivatives of these individually. And so where do we end up? We end up with the vector valued function r would be, let's see, do that antiderivative, we'd have 1/2 sine 2t plus a constant. And then the antiderivative of that one would be 2 cosine t plus a constant. It's a goofy looking t, isn't it? but we had an initial condition, so we want to use, so now we want to use the fact that if you plug in 0, the output should be 3, -2. So let's go do that. So I should get 3 when I plug in 0 here. Sine of 0 is 0, so C1 needs to be 3. Then the output should be -2 for this component. Except for I'm plugging in 0, aren't I, for t? So -4 should be the second constant. So it turns out that the vector valued function that we wanted is 1/2 sine of 2t plus 3, comma 2 cosine t minus 4. So that's the particular vector value function that has that derivative and contains that initial condition of 3 comma -2. Okay, the only other thing that needs mentioning is now that we know how to do derivatives, we can do motion. We can talk about an object that's moving along one of these curves. So what if we let a vector valued function r, instead of f and g, I'm going to use x and y. Switch things up here. So we're going to let the vector valued function r be the position function for some object in motion. So if you were to graph the vector valued function r, it would show the path of motion. So basically it would allow you to locate the object for some value of t. Well, just like we're used to with regular functions, if I then want velocity for that object, we could just call that v, except for it to be a vector valued function, v, and we would find it by just doing the derivative of r. Simple as that, just like we normally would. Derivative of position is velocity. And then if you wanted acceleration, again, no surprise here, we could call that vector valued function a, and that would just simply be the derivative of velocity, or another way to think of it, second derivative of position. Again, no surprise, exactly as it worked for a traditional function. And then if you wanted the speed, this will be a little different because we do have vectors involved. Turns out if you want the speed of the object for some value of t, you would do the principal square root of x prime t squared plus y prime t squared. If you're familiar with vectors at all, I don't know how much vectors you guys have done in other classes, but this is essentially the magnitude of the velocity vector. So this is the magnitude of the velocity vector. So we do get kind of a new formula. If you're not real familiar with vectors, this is yet another formula you're going to have to know, but it's not too difficult to remember.